Hello everyone, welcome back. So today we'll continue with the theory part of this class, and we're going to do a new topic. So this will be kind of a change of pace compared to what we've been doing before, and which is plane waves. So maybe you've seen plane waves in an undergraduate EM class, but we'll go a little bit deeper in today's lecture and the next lecture. And we'll see that it's a lot of interesting phenomena you can observe when you kind of look at plane waves and how they behave. Okay, so we'll start with plane waves in homogeneous medium, and then we'll look at more complicated cases later, but this is sort of an introduction to plane waves. Okay, so we can start from Maxwell's equations. So this is the time harmonic form of Maxwell's equations, and we're in a source-free region. So we want to look at what kind of solutions we can get to Maxwell's equations in a source-free region. And we'll see that one of the solutions is this plane wave solution. Okay, so these are Maxwell's equations in a homogeneous isotropic source-free region. Source-free, time harmonic, Maxwell's equations. Okay, so from this you can show that curl of E is equal to I omega mu curl of H, which is of course minus I omega epsilon E, right? So this gives me omega square mu epsilon E, and that I can write as K square E. Okay, where K square is omega square mu epsilon. We've seen that before, and K is the wave number. And then we also know that this is nothing but gradient of divergence of E minus Laplacian of E, vector Laplacian, right? But this is zero because the divergence of E is zero. So this implies that vector Laplacian of E plus K square E equal to zero, right? And that's the wave equation, vector wave equation, when you have a divergence-free vector field. Okay? All right, so we are looking for solutions to this vector wave equation in a homogeneous medium. And the simplest solution is of this form. E equal to E naught psi of R. Right? So it's some constant vector, and that constant vector has an amplitude modulation given by psi of R. Right? So it looks something like this. It's all pointing in the same direction, but the value itself is changing, right? Depending on where you are. Something like that, right? Okay, so this is sort of the simplest solution that we can think of. So you substitute this back into, so you substitute this into that, and then you see what you get. Okay, so what do you get? If you substitute it, you will get E naught vector Laplacian of psi of R plus K square psi of R equal to 0. Of course, if you want this to be true for any E naught, for an arbitrary E naught, then you need the Laplace, the scalar wave equation to be true, right? You want this to be equal to 0. Okay, so essentially we want to solve the scalar wave equation. Okay, so the solution we're going to look for uses this technique called separation of variables. And we'll use this again and again in different contexts. Okay, so what does that mean? So I know psi is a function of R, but I want to say that this can be written as three functions, product of three functions, such that each of them is only a function of one of the variables. Right? So it's x of x, y of y, times z of z. Okay, so essentially, this is a specific type of solution that we're looking for, a solution that can be separated into these three factors. right? Where each factor is only a function of one of the variables, x, y, or z. So now you may say, okay, no, this is not general enough, right? This doesn't give you all the solutions. And that's true. But later we'll show that the solutions you get from this form a basis to all solutions to this wave equation. Okay, so essentially from this we'll get what is known as plane waves. And we show that plane waves indeed form a basis, which means that any solution can be written as some combination of these kind of solutions. Okay. All right. So we substitute this, this into this equation, set it to 0, and then see what we get. So essentially we have Laplacian of capital XYZ plus k square capital XYZ equal to 0. And then I'll divide by this capital XYZ on both sides. Then what do you get? If I take Laplacian of this factor, you can use product rule. That would be yz times Laplacian of this plus xz times Laplacian of y plus xy times Laplacian of z, right? And then when you apply Laplacian to this, then what do you get? Right, so essentially you will get something like yz divided by xyz, and Laplacian of x is nothing but d square over dx square x, right? So that essentially becomes, so I'll write it out, yz over xyz, d square over dx square. So this should be little x, dx square capital X, right? But this is nothing but 1 over x, right? So I'm going to write it as 1 over x. And similarly, the other two terms, 1 over capital Y, d square dy square y, plus 1 over capital Z, d square dz square z, plus k square equal to 0. Okay? So now, since each of these terms, this term is only a function of x, this term is only a function of y, and this term is only a function of z, for the summation to be equal to minus k square, a constant, it has to be true that each of them must be a constant, right? Because if this is not a constant, which means if this is a function of x, then this cannot be a function of x, and this cannot be a function of x, which means it cannot be equal to a constant, right? So only if each of them is a constant, you can have the summation to be a constant. And that's why separation of variables is a powerful technique, because it allows you to separate these equations this way. So we'll call each constant d square over dx square x equal to minus kx square. Similarly, you have 1 over y, d square over dy square, capital Y equal to minus ky square, and 1 over z, d square over dz square, capital Z equal to kz square. Okay, so putting all of these together, we get kx square plus ky square plus kz square equal to k square. Well, this is a very important relationship. This is known as the dispersion relation of free space. Okay, and we'll see why maybe it's called that later on. But essentially, these constants have to satisfy this relationship, right? X, y, kx, ky, kz have to satisfy this relationship. So we know the solution to this differential equation, right? That's pretty trivial. So the solution to that is nothing but e to the I kxx, right? Because you take derivatives and you substitute it in here, that's what you will get. Okay, you get ikx times ikx, which becomes minus kx squared. And then when you divide by e to the ikx, it cancels out the e to the ikx, and you end up with minus k squared, kx squared, which is what you have on the right-hand side. Okay, similarly, y is equal to e to the I kYy, and z equal to e to the I kzz. Okay. So now that we have this, we can substitute xyz into into psi, sorry, psi, and then substitute psi back into this, and that gives you the final electric field solution, right? So the electric field now, the function of r is E naught e to the I k dot r, which is equal to, or instead I should write it explicitly and then define this k vector. It is e to the I kxx plus kyy plus kzz. And that's exactly these three terms. This is your psi of r. Okay. So now this I can write as E naught vector e to the I k vector times r vector, where my k vector is kx x hat plus ky y hat plus kz z hat. Okay, you substitute that in here, in Cartesian coordinates, that gives you exactly this, which is what we want. Right, so this equation, E of r equal to this is what represents a plane wave. Okay, I need to do that again. So let me move this. We put it in a red box. Okay. So this is known as a plane wave. We use this. The solution is called a plane wave solution, and we'll see why it's called a plane wave. Okay. So I should write again that k vector is kx x hat plus ky y hat plus kz z hat. Okay, and modulus of k is square root of kx squared plus ky squared plus kz squared, and that is nothing but k from the dispersion relation. Right, so essentially we've generalized this k, which was 2 pi by lambda, into a k vector, right? Vector k. And that's called the wave vector. And we'll see what this means, what it signifies, and so on and so forth. But this wave vector is associated with every plane wave. Okay. Okay, so let's actually do that now. So what is this wave vector, right? So k is 2 pi by lambda. This represents spatial frequency. Spatial frequency, right? So by spatial frequency, we know that time frequency is omega, which is the number of times, the signal went up and down in a given second. Spatial frequency represents how many times the signal went, the wave, for example, has gone up and down in 1 meter. Right? So if the spatial frequency is high, that means its wave is like that in space. If the spatial frequency is low, it's changing very slowly in space. Okay, so it's kind of how fast the wave is changing in space. We are more familiar maybe with f or omega, where it represents how fast the wave is changing in time. Right? And that relationship between how fast it's changing in space and time is given by the velocity of the wave. Right? So k is equal to omega over v, which is the wave velocity. Okay, so this is time frequency, this is spatial frequency, and this is the velocity. Then what is this vector k? Right? So the vector k determines which direction the phase is changing in. Okay. So we know, for example, if you go back to time domain, omega is nothing but the time derivative of the phase, right? That's how it's defined. That's what frequency means, really. So K should then be the spatial derivative of the phase, right? How fast it's changing in space. So one way to kind of represent that is to take the gradient of the phase. But what is the phase? For a plane wave, the phase is just K dot R, right? And that's exactly what you get. If you take the gradient of K dot R, you get back K, right? So it's telling you which direction the phase is changing the fastest. That's what this K vector means. Okay, another way to look at it is visually. So this also explains why it's called a plane wave. So for example, if I look at this phase factor here and I want to look at surfaces of constant phase, right? So surfaces of constant phase. Okay, so say my K vector is something like that. That's my K vector. And I want to find which surface has a constant phase, which means I need to find all the points, all R vectors, such that K dot R is constant. And what are those vectors? Right, those are all these vectors. Because their projections onto A all have a constant value. Right? So when you project all of these vectors onto K, you get all of these vectors that lie on this surface, which is normal to K. Right? So there is a single surface that's normal to this K vector, and all R vectors that lie, position vectors that lie on that surface have the same projection onto K, which is the same K dot R value. Right? Which means that on this surface, all these vectors have the same phase. So surfaces of constant phase are planes. Planes normal to K. That's the reason this solution is called a plane wave solution. Okay. So if you actually plot it, we'll actually do an example next. Okay, so let's take some examples and try to understand what is this plane wave, what is K a little bit better. Okay, so let's say I'm in real space, right? And my X and Y axis are here, just drawing X and Y. So if I have a plane wave, that means planes of constant phase look something like this. So let's say I'm drawing the maximum of the wave, right? Where the phase is, I don't know, some 0 degrees maybe, or something like that. The wave is something like this, right? It's propagating this way. So what does this mean? This is the wavelength because it corresponds to 2 points that have the same phase, right? So if this was my wave, then, or maybe I should draw one, a few more cycles. Then essentially this point and this point have the same phase, right? So you can imagine I'm drawing the maxima when I'm drawing these lines. Okay, so this is the wavelength, right? So wavelength is nothing but 2 pi by K, right? Then what is this? The wavelength along X is actually 2 pi by Kx. That's what Kx means. It is the wave number along the X dimension. And this length is 2 pi by Ky. Okay, so it's the wavelength along the Y dimension. Corresponds to the wavelength along the Y dimension. That's in real space. But now if I take this and I can also plot the same plane wave in what is known as K space. So Kx, Ky, Kz also form a space. And so this is Kx, this is Ky. For this given plane wave, which has this Kx value and this Ky value, I can take this Kx and find where it is along this line. Maybe it's somewhere there, and my Ky is somewhere there, right? And they both look almost the same. So if I plot it in K space, it's a single point, right? So a plane wave in real space corresponds to a single point in K space. It's similar to how you have a sinusoid in real time, time domain becomes a single frequency or a single point in the frequency domain. This is the three-dimensional analog of it. A single plane wave in real space becomes a single point in K space. So similar to like how, for example, it's much easier to deal with many concepts in frequency domain when we do electrical engineering or signals, right? I mean, for example, impedance is done in frequency domain, Bode plots done in frequency domain, transfer functions done in frequency domain, and so on and so forth. Similarly, many times it becomes easier to think about electromagnetic fields or concepts like this in terms of the K space, where you think about what does the spectrum of this electromagnetic field look like in K space. Right? So if I have a bunch of plane waves, it can have a very complicated distribution in real space, but in K space, it would just be a collection of points, right? So now if I can take this one step further, now if I draw a vector here that has that length, then the length of this vector would be K, and the direction of this vector would be the K vector. So this is exactly the K vector, in fact. So here the K vector is like this, right? It's a plane wave propagating in that direction. And in K space, it corresponds to this point here, and this vector that points to that point, right? So the K vector essentially tells you in which direction the phase is growing or phase is propagating. And in K space, corresponds to a location which gives the Kx, Ky, and Kz values. So let's take another example. So once again, I'll draw the real space. XY. And my plane wave, let's say, is propagating like this, right? At a very steep angle. Draw a long line. Something like that. And we can extend our x-axis a bit more. This intersects somewhere here. Okay, which means what? Now my kx is giving this length. This is 2 pi by kx. And this is 2 pi by ky. Right? And the direction of propagation now is, we know it's in this direction. And this length is always the same. This is 2 pi by k. So now if I plot this in k space, what does it look like? So there's two ways to do it. We know the direction of propagation and we know the length of k. So we can directly draw the k vector. But instead, let's do it with kx and ky. So kx must be very small for 2 pi by kx to be large. Right? So my kx is somewhere here. So this axis is kx, this axis is ky. And ky should be kind of large, almost close to k, because it's almost exactly the same as, so this length is about the same as the perpendicular distance between these two lines, right? So my ky have to be kind of large. Let's say if I plot this point somewhere here, and if I plot the vector, of course, it's the same as the vector I drew back there. Okay, so you can kind of see that this kx and ky as this plane wave, is in this direction or this direction or this direction and so on. They trace out a circle at a given k, at a given frequency, right? And that's exactly right. So for different values, these points would lie on the circle. And each point on this circle corresponds to a plane wave in a given direction. Corresponds to a plane wave in a given direction. Why do they have to lie on a circle? Because we know that kx squared plus ky squared plus kz squared is equal to k squared. That's one way to look at it. Another way to look at it is that, okay, plane wave, each of them corresponds to a plane wave. It's going in different directions. Then that has to correspond to basically k's that trace out a circle, right? When k is fixed, which means the frequency is fixed, right? Because k is omega over c. Okay. And of course, you can also see that mathematically from this equation, which is the dispersion relation, right? So in 3D, of course, it's not a circle, it's a sphere, because you also have kz. So you have kx, you have ky, you also have kz. Here I've only drawn the kx and ky case, which means I will assume kz to be 0. So you have plane wave that's propagating in the xy plane. But in reality, this whole thing is a sphere. Okay? So all of these points, all these waves, essentially propagate such that plane waves going in different directions, propagating in different directions, corresponds to points lying on a sphere. Okay. Now you could ask the question, do points have to lie on the sphere? This is the equation for a sphere, that's true. But that is only true when kx, ky, and kz are real quantities. So if they're real quantities, then this is satisfied by, this essentially describes the equation for a sphere. But we can take this a little bit further and allow kx, ky, and kz to be complex quantities or real or imaginary quantities. So then what do you get? And we'll see what that means. So if I assume kx squared plus ky squared is greater than k squared, that implies that kz is I square root of kx squared plus ky squared minus k squared. Right, and of course now this is greater than 0, so this whole thing is real, which means kz becomes imaginary. So what does it mean for kz to become imaginary? Right, my e, if I go back to it, I have e naught, e to the I, kxx plus kyy plus I, kzz. But kz is imaginary, so that becomes minus kzz. I should write it as minus, let me say kz prime z, or kz double prime z, right? Where kz was I kz double prime. Okay, so what does this mean? This looks like exponential decay in the amplitude. So if I rewrite this, I get e naught, e to the minus kz double prime z, e to the I kxx plus kyy times e naught hat. Right, so this is a valid solution to the wave equation, because in the derivation of the wave equation, we never said that kx, ky, kz need to be real. Right, we left it ambiguous. Now we are considering the case where it's not real, where it can be imaginary. So let me box. Okay, so these waves are called evanescent waves. So evanescent means something that's short-lived, right? They're evanescent because they exponentially decay in the z direction. So what does that mean? So I have a wave that is decaying exponentially along the z direction, and along the x and y direction, the phase is increasing. So phase is changing along the x and y direction. So it's maybe propagating in that direction, but it decays exponentially in this direction. And this can exist, this exponential decay can exist even in a lossless medium. So that doesn't mean that there is loss in the medium. Even in a lossless medium, you can have a solution for a wave that decays exponentially. It's a valid solution to the wave equation. That's what it means. Okay, we'll revisit evanescent waves in the next lecture and look at many of their interesting properties, how do you excite them, and so on and so forth. That's a whole different topic. But I just wanted to kind of introduce you to what they are and show you that, it's a valid solution to the wave equation. Okay, we want to look at some of these other properties. So we looked at the gradient of the phase and showed that that's equal to k. We can also establish a few more relationships in plane waves. So one of them is by taking the divergence of E, which we know is 0 from Maxwell's equations. And the divergence of E, when you put the plane wave equation in there, is nothing but E naught vector times the gradient of E to the I k dot r. Okay, and that comes from your vector identities of divergence of a vector times a scalar, right, where the vector is E naught and the scalar is the E to the I k dot r. And this becomes nothing but E naught dotted with I k e to the I k dot r. And this is 0 from Maxwell's equations, right? Which means what? Which means that E dot k must be 0 because r is an arbitrary quantity. And we know k dot r is not equal to 0. So if E dot k must be 0, that means that E naught is always perpendicular to k. So the direction of polarization, the direction of the vector electric field, is always perpendicular to k. We can also get some more information by considering h, which we know is minus I over k eta, where eta is square root of mu over epsilon, right? Curl of E, which is E naught e to the I k dot r. Right, so this is nothing but minus I over k eta times curl of vector times a scalar. You can also do it. Turns out to be ik cross E naught times e to the I k dot r. Okay, and that is equal to nothing but k hat cross E naught over eta. I and minus I cancel. K vector over k is k hat. And then you have the 1 over eta. E to the ik dot r. So what does this mean? This means that h is now perpendicular to E, which was perpendicular to k vector, k hat. This is an important relationship. So in a plane wave, the electric field, magnetic field, and k vector are all perpendicular to each other. Okay? And we look at mod E over mod H. The magnitudes, that is equal to eta, which is equal to square root of mu over epsilon. And this is 377 for free space, where you have mu naught and epsilon naught. Free space. And that's why this eta is known as the free space wave impedance. Impedance of free space. Right, so essentially we're saying that in a plane wave, the magnitude of electric field and magnetic field is always constant. The ratio is always constant. And that constant is 377, which we call an impedance because it is in fact the ratio of an electric field and a magnetic field, similar to the ratio of V over I, right? That's called free space impedance. Okay, so that's a nice introduction to plane waves, and hopefully it clarifies some questions about this k vector and also k space and where all of this comes from. So we can take this one step further and actually look at what is known as the plane wave basis. Okay, so similar to how you can take a Fourier transform of a given field or a given signal in time domain, you can also take a three-dimensional Fourier transform in space. So if I have a vector field, E of R, this is rather the inverse Fourier transform, Kx, Ky, Kz, E vector tilde, Kx, Ky, Kz, e to the ikxx plus I kyy plus I kzz dkx dky dkz. This is a three-dimensional Fourier transform or inverse Fourier transform rather, because we're going from k space to real space. So if it was one-dimensional and time domain, this would be E of omega, this would be E of t. So this is nothing but mathematical relationship. We haven't done anything beyond that. Right? I've only written down a mathematical relationship where I'm expanding E in terms of its Fourier transform. Okay, I can rewrite this as integral over vector k, which represents nothing but this triple integral. So notation E vector tilde of k e to the I k dot r dk. This is my E of r. So what does this represent? This is nothing but the k-space representation of your electric field. So given an electric field in space, a function of space, I can take its three-dimensional Fourier transform, and that gives me the same vector field in k-space now. And so earlier we saw a plane wave in k-space is a single point, similar to how a sinusoid is a single point in frequency. But you can take any time domain signal and convert it to frequency domain. Similarly, you can take any electric field and convert it into a k-space representation, right? Which is this one. Okay, but this is for an arbitrary electric field. So this electric field can be arbitrary, which means that it can be anything. It doesn't have to satisfy any continuity, doesn't have to satisfy any wave equation, nothing. Because this is just a simple mathematical relationship. So this doesn't even have to be electric field, it can be any vector field. That's arbitrary. But we know, right? So I'll say this is for an arbitrary vector field. Okay, but electric field has to satisfy the wave equation. Free space, but E must satisfy the wave equation. Okay, so it cannot be arbitrary, it has to have some structure to it, right? So essentially the wave equation that electric field satisfies gives us the dispersion relation, right? Kx squared plus ky squared plus kz squared equal to k squared. Okay, so in other words, now I can say kz, and you can choose any of them. It doesn't, kz is just an example, can be written as k squared minus kx squared minus ky squared. So that's a big constraint, which means that this is kz is not an independent variable anymore, right? So in your typical 3D Fourier transform, kx, ky, kz are independent quantities, right? But in our case, because we have this wave equation, kz is not independent. It is in fact dependent on x and y, which means this integral is not a three-dimensional integral, it's actually a two-dimensional integral. You don't have an independent variable here. So what do you get? So that becomes E of xyz is integral over kx, integral over ky, E tilde kx comma ky. It's only a function of x and y, kx, ky. You have your e to the I kz z, right, where kz is given by this. So it's not a function of, it's not an independent variable. This whole thing times e to the I axx, e to the I ayy, dkx, dky. Okay. So what does this actually look like? Right? This is in fact saying that given an electric field in real space, in K space, if I specify just this quantity, what is the value of E tilde as a function of Kx and Ky? From that, I can fully reconstruct the electric field. So this quantity is known as the angular spectrum or the K-space spectrum or K-space spectrum. Similar to how you have like an omega spectrum for a given signal. In K-space, it's a two-dimensional spectrum. It's only a function of Kx and Ky. And we also saw this a little bit, right? Earlier, we said that all of these plane waves have to lie on the surface of a sphere. And we showed that, okay, plane waves form a basis, which means that any signal that you have has to be some combination of points that lie on the surface of the sphere, right? And that surface of a sphere is a two-dimensional quantity. It's not a 3D quantity, right? So that exactly tells you that your angular spectrum and K-space spectrum are that two-dimensional quantity. It's the specification of points on a sphere which gives you your total signal. So knowing this is enough to know your entire electric field. Okay, so how is this useful? This is very useful because, for example, if I know the spectrum, let's say I have the electric field in some aperture. So at the aperture, I know the electric field. I don't know it everywhere. If I know the electric field at the aperture, then I use that to find what the spectrum is, kx and ky. Right? And there's a way to do that. Essentially, you have to do an inverse Fourier transform, or you have to do a forward Fourier transform to do that. Once you have the spectrum here, you have this, which means you can put that into this integral and find the field at any point z, right? At any point outside. So essentially, from a known field, you can find in a known location, in a given location, you can find this. And once you know this, then you can find the field anywhere else in space. And that's very powerful, right? So that's called the angular spectrum. Okay, so this angular spectrum, so far we've been saying it lies on the surface of a sphere and so on and so forth, but that's only true when you have propagating waves. If you have evanescent waves like we saw, then you don't lie on the surface of the sphere anymore, right? Because for an evanescent wave, we saw that kx squared plus ky squared can be greater than k squared. So I can have a point out here, and if the point is out here, which means it's greater than this k squared, then kz becomes imaginary. Right? So complex values of kx, ky, and kz, they don't lie only on the surface of the sphere. And you can actually have points outside the sphere as well. You cannot have points inside the sphere, but points outside the sphere corresponds to the evanescent part of the spectrum. Points on the sphere correspond to propagating spectrum or the propagating part of the spectrum. Okay? Okay. So let's write that down. So the angular spectrum itself has a propagating part. Just to repeat myself, the propagating part lies on the surface of the sphere, propagating sphere, and it has an evanescent part, which is the part that lies outside that sphere in K space. Okay, so it can include both. And you really need both in many cases if you want to fully represent this electric field. Okay. So from this, we can actually derive a very fundamental result, which is the diffraction limit. Sometimes it's called the Abbey diffraction limit. Simple. Okay. So we know from the properties of Fourier transform that if I have a real signal that is a step function, not a step function, I guess a pulse function like that, or a square function, then its Fourier transform is a sinc function, right? And the property is that if this width is delta x, this width is delta kx or delta kx, then properties of Fourier transforms tells us that delta x times delta kx is equal to 2 pi. And we know that, right? So if I have a very broad pulse, then in frequency domain, the sinc function becomes narrower and narrower, right? Because the product of the two is a constant. Okay, so this is actually where Heisenberg's uncertainty principle also comes from. But anyway, we don't have to get into that. But this is a very fundamental relationship. Okay, so now if we go back to our optics or electromagnetics, then if I look at the, if I only have propagating waves, you have propagating waves, that means what? That means that in K space, right, you're on the surface of that sphere. So this is x, kx, ky, and there is the sphere, right? You only have the sphere, you don't have the evanescent spectrum, which means the maximum value that kx can take, the maximum kx that you can have, goes from minus k to k. This is minus k and this is plus k, right? So maximum value of kx is equal to 2k. And we know that the product of, so essentially this is saying that if I have plane waves that are propagating in all these directions, I have this entire plane wave spectrum, right, that's propagating. Then if I look at the smallest value of delta x, right, which means, okay, if I have, let's say I have a lens, and this lens is focusing these waves down to a single spot, right? Then at that spot, the maximum k you can have can only go from minus k to k in the x dimension, right? Which means the smallest size of the spot, the minimum value of x, delta x, is given by 2k, is given by 2 pi divided by the maximum value of kx, right? Because kx times delta x is 2 pi. So when kx becomes maximum, delta x becomes minimum. And what is that? So delta x min is 2 pi divided by 2k, right? And 2k is 4 pi by lambda. So that becomes lambda over 2. Okay. So essentially this is saying that, if I have a lens, and this has to be an infinitely large lens, only then it can produce, only then it can have waves that propagate along x, right? So if this is my, maybe I should draw that out. I have an infinitely large lens, very large lens, right? And this is my x dimension. Then this infinitely large lens can produce waves going out like that, right? And you're focusing very close by. So it has waves, all these waves exist. This one is approximately equal to something that's propagating only along x, right? This one is approximately equal to something that's propagating along minus x. Or I should say, this wave that's coming in here is something that's close to positive x. Right? Maybe it's like that. And this wave coming down here is something close to negative x. Right? And if this lens is in fact infinitely large, then it can produce rays that are coming straight down this way and this way, and you're focusing right in between. Right? Then you can have this wave and this wave, but still the spot that you can produce cannot be less than lambda over 2 because of this relationship. So even an infinitely large lens cannot produce a spot size that is less than lambda over 2. Okay, and that's called the diffraction limit. This is, of course, assuming you don't have any evanescent spectrum, because if you have evanescent spectrum, then the maximum K can be larger than that. Right? So only for propagating waves, this is true. This is very important because if, let's say, you want to make a radar system, right? You have an object, and that object scatters waves, and then you measure all these scattered waves, right? All of these scattered waves carry scattering information of that object, right? But if you can only measure the propagating spectrum, because the evanescent spectrum is not measured, you're very far away from the object. If you're only measuring the propagating spectrum, then you're only measuring these propagating waves, which means the best resolution you can get is always limited by lambda over 2. So if you can make an imaging system that has this resolution, then that imaging system is called diffraction limited. Okay? So does this mean that we are doomed, that we can never make imaging systems that are less than this? The answer to that is no. So there are a few assumptions that we've made so far. Right? And breaking those assumptions can give us some hope of breaking this diffraction limit. Okay? So one way to break it is, of course, to access the evanescent spectrum. And there are many technologies that do that. So one of them is near field microscopy. So the idea here is that, okay, if you have some kind of microscopic sample that's very small and you want to be able to see these variations that are less than lambda over 2, then you can shine some light on this, right? And then bring a probe that's very, very close to this object, such that the evanescent waves that are scattered from this object hit this probe and then get radiated out into the far field. And then in the far field, you kind of measure those radiated fields from this probe. And then from that, you're essentially able to reconstruct the evanescent spectrum that got scattered from this sample. It, of course, is a very high-level simplification. In reality, it's not that simple. You need to know what the probe is, how does it scatter, how does it scatter the evanescent spectrum, and so on and so forth. But that's the general idea, is that this evanescent spectrum that would have decayed exponentially now couples to this probe and then radiates from the probe to the far field, and then you capture it in the far field. So you're essentially scattering the evanescent spectrum into the far field. Okay. Another way to do it, which received a lot of its attention over the last few years, is to use what is called a negative index lens. We haven't really discussed it in this class. You're welcome to kind of look it up. But essentially, it's a flat lens where epsilon is less than 0 and mu is less than 0. So when epsilon and mu are less than 0, we had I e to the I az double prime z, right? This, in fact, we had e to the I kzz. So we said that kz becomes imaginary because of the fact that kx and ky are greater than k. But in a negative index medium, kz is already imaginary. Okay, so you get essentially a cancellation of i's. So you get I times kz double prime. Then these go away. Is that right? So you don't get I times I, you get a negative I. Yeah. So instead of positive I, you get a negative I. So you get, when you do I times I, you get a -1, and this becomes plus kz double prime z. And that's what a negative index medium does. So what happens? You have a ray, wave, that evanescent wave, say this is your object, your evanescent wave was decaying, and then it starts to grow inside this lens. And then again decays as it propagates outside the lens. Right? So then that essentially allows you to measure these fields out here because they've grown quite a bit and they're not below the SNR of your or the noise figure of your receiver. Right? So you can still receive it and measure these waves. That's the idea behind negative index lens. So making the negative index lens is the hard part. But if you do have something like that, then you can do this kind of measurement. Okay? So that's one way is to essentially access this evanescent spectrum. But let's say you can't access it, then what do you do? If you cannot access it, then the only way to do it is to have a priori knowledge of the target. Or I should say, rather than a priori knowledge, I should say additional knowledge. It can be a priori, it can be part of your measurement setup. Additional information, I should say, rather. Of the target. Okay, so what are examples of this? The first one, which I like to give, is magnetic resonance imaging, MRI. So if you actually look at MRI, right, it's usually no more than 200 megahertz or so, which is the MR signal. And even if it's at 1 gigahertz, what's the wavelength at 1 gigahertz is 30 centimeters, which means the diffraction limit should be only 15 centimeters. And so by measuring MR signals, you should not be able to resolve less than 15 centimeters. But we know that MRI can get down to even sub-millimeter, right? Hundreds of microns of resolution. How does it do that? The way it does that is that it modulates the target. So if I have a target sitting like that, by applying magnetic gradients, I apply a gradient like that, and that essentially slices your target into different slices where, based on the strength of the gradient, you have a different frequency that's radiating. Right? So all of these points, they radiate at slightly different frequencies. So essentially you have additional information. You know that if you're measuring a signal frequency, you know that that came from this slice, right? Or if you're measuring at this frequency, it came from this slice. This frequency came from this slice, and so on. Right? So you have additional information that, okay, if I'm measuring a certain frequency, what was the slice from which it came, right? And then you do these gradients in different directions. Then essentially you slice up your target different ways. And then from all of those slices, you can pinpoint from which point that given radiation came from. Okay, so you're essentially modulating your target using these magnetic gradients in order to break the diffraction limit. So it's giving you additional information of the target. So you're not limited by the resolution of MRI. And of course, MRI, brilliant idea, won the Nobel Prize in 2003. So breaking the diffraction limit can essentially give you a Nobel Prize. Of course, I'm oversimplifying and being a bit facetious, but the idea itself is that you're not always limited by the diffraction limit if you're clever enough. Another technology that does that is fluorescence microscopy. Yeah, so it's a similar idea to MRI, at least from this perspective. So if I have some target that is much smaller than the resolution of my lens, then you can add a fluorescent dye to part of it, and then you image this target when the fluorescent dye is turned on and turned off. Right? So in one case you have that image, in the other case you have the whole thing. So you can essentially separate this part and this part by turning on and turning off different regions of this object using a fluorescent dye. Which is again like modulating your target in some way. Right? So that also breaks the diffraction limit. And this won a Nobel Prize in 2014. So this is a very simplified version of what exactly fluorescence microscopy is. But I just want to show you that it's somewhat connected to this idea of diffraction limit and breaking the diffraction limit. Okay. There are other ways as well. So spectral estimation techniques is another one. So the idea behind spectral estimation is that, okay, you're not modulating the target, but you know a priori something about the target, right? So you know, for example, that is sparse. And that comes down to algorithms like music, Esprit. This is more like in imaging and signals and so on, or compressed sensing. Right? All of these techniques essentially say that, okay, we know something about the target. Maybe it's sparse in either real space or it's sparse in some domain or in some representation. And then from that extra information, I can form an image of my target without having to actually be limited by this diffraction limit. Right? So it's really not breaking fundamentally the diffraction limit. It is in some sense exploiting the fact that, okay, when it's sparse, I can go beyond that. So for example, if you have two targets next to each other, even though they're less than the diffraction limit of your imaging system, you can still image them. But if I have 10 targets, then it may not work, right? So you need to be a bit careful when using these techniques. And similar to these kind of spectral estimation, it also includes deconvolution. So all of these techniques kind of rely on the fact that you have some additional information. Okay? Okay, so maybe we will stop here and continue plane waves in the next lecture. But just to recap, we started with defining plane waves, not defining, I guess, but started with homogeneous medium, derived the wave equation, did separation of variables, and derived the dispersion relation of plane waves. And we showed that plane wave solution is one of the solutions. We described why it's a plane wave. We looked at this k vector, and then we looked at different examples of what plane waves look like in real space and k space. We described evanescent waves. We made K complex, which we'll revisit in the next lecture in more detail. Then we looked at the plane wave basis and how that leads to this angular spectrum representation of a given electric field. And then we also looked at the diffraction limit that arises from the K space. Then we looked at some examples of breaking the diffraction limit that people have done in the past. Okay, hopefully that was an interesting lecture, and we'll stop here. In the next one, we will go a little bit deeper into plane waves, discuss how plane waves propagation takes place in lossy media and also in anisotropic media. Okay, thank you. I'll see you in the next one.